The National Electrical Code, or NEC, does require a grounding rod to be driven at the meter socket in the described situation. This requirement is based on specific sections within the NEC that define the grounding electrode system and its components. According to NEC 250.68d, a grounding electrode system must include one or more grounding electrodes installed in accordance with 250.52 ATWA through E8, and a grounding electrode conductor connected to these grounding electrodes. Now let's delve into NEC 250.52 A7, which specifically addresses rod and pipe electrodes. This section mandates that a grounding electrode, which could be a rod or pipe, must be driven into the earth at least 8 feet at the service equipment location. In the scenario presented, the service equipment is located at the meter socket. This means that a grounding rod is indeed required to be driven at that location to comply with the NEC. The authority having jurisdiction, or OJ, is therefore correct in requiring a grounding rod at the meter socket, ensuring adherence to the NEC grounding standards. The purpose of a grounding electrode system is to provide a low impedance path for fault current to return to the source, which helps to trap the overcurrent protective device such as a circuit breaker or fuse. This is crucial for safety, as it minimizes the risk of electrical shock and fire hazards. The grounding electrode system also helps to stabilize the voltage to ground during normal operation. There are several types of grounding electrodes that are recognized by the NEC. These include rod electrodes, pipe electrodes, plate electrodes, concrete encased electrodes, ground rings, and other listed electrodes. The selection of the appropriate grounding electrode depends on various factors such as soil conditions, local codes, and the specific requirements of the electrical system. Rod electrodes are commonly used and consist of metal rods, typically made of copper or galvanized steel, that are driven into the ground. Pipe electrodes are similar to rod electrodes but are made of metal pipes. Plate electrodes are metal plates that are buried in the ground. Concrete encased electrodes, also known as UFA grounds, are grounding electrodes that are encased in concrete, such as the concrete foundation of a building. Ground rings are bare copper conductors that are buried in a circular or loop configuration around a building. The NEC provides detailed requirements for the installation of each type of grounding electrode. These requirements include the size of the electrode, the depth at which it must be buried, and the spacing between multiple electrodes. For example, NEC 250.53G specifies the requirements for the supplemental grounding electrode. If a single rod, pipe, or plate electrode does not have a resistance to ground of 25 ohms or less, it must be supplemented by an additional electrode. The supplemental electrode can be another rod, pipe, or plate electrode, or it can be a concrete encased electrode or a ground ring. The grounding electrode conductor, or GEC, is the conductor that connects the grounding electrode to the service equipment. The GEC must be sized in accordance with NEC 250.66, which provides tables for determining the minimum size of the GEC based on the size of the service entrance conductors. The GEC must be securely connected to the grounding electrode in the service equipment. The connection to the grounding electrode must be made using a listed connector or by exothermic welding. The connection to the service equipment must be made at the neutral bus or ground bus in the service panel. In the specific scenario described, the service is a single-phase residential 120/240 volts, 200 amps underground service. The meter socket is located on a post in the yard, and the utility company and the customer's neutral conductors are bonded to the meter enclosure. The underground service lateral consists of 3 conductors and runs to the main breaker in the residential panel board. A number 4 bay grounding electrode conductor connects the panel board to the concrete encased electrode in the footer. Given these details, the requirement for a grounding rod at the meter socket is further reinforced by the NEC emphasis on establishing a comprehensive grounding system at the service equipment. The meter socket, being the point where the electrical service enters the premises, is considered part of the service equipment. Therefore, it must have its own grounding electrode. The grounding electrode conductor from the meter socket should be connected to the grounding electrode, which in this case is the grounding rod driven at the meter socket location. This ensures that the meter socket is properly grounded, providing a path for fault current to flow back to the source. The existing concrete encased electrode in the footer, while serving as part of the overall grounding system, does not negate the requirement for a grounding rod at the meter socket. The NEC intends for multiple grounding electrodes to be used to create a more robust and effective grounding system. The concrete encased electrode helps to reduce the overall resistance to ground, while the grounding rod at the meter socket provides a local grounding point for the service equipment. It's important to note that the NEC is a minimum standard, and local codes may have additional requirements. In some jurisdictions, the AHJ may require additional grounding electrodes or more stringent grounding practices. It's always best to check with the local AHJ to ensure compliance with all applicable codes and regulations. In summary, the NEC requires a grounding rod to be driven at the meter socket in the described situation. This requirement is based on NEC 250.68D and 250.52 A7, which mandate a grounding electrode at the service equipment location. The AHJ is correct in requiring a grounding rod at the meter socket, ensuring compliance with the NEC grounding standards. Understanding and adhering to these grounding requirements is essential for electrical safety and for ensuring the proper operation of electrical systems. First, always consult the latest edition of the NEC and any applicable local codes before performing any electrical work. Second, ensure that all grounding electrodes and grounding electrode conductors are properly sized and installed in accordance with the NEC. Third, verify that all connections are secure and made using listed connectors or by exothermic welding. Fourth, consider using multiple grounding electrodes to create a more robust and effective grounding system. Fifth, if you are unsure about any aspect of the grounding requirements, consult with a qualified electrical contractor or engineer. Grounding is a critical aspect of electrical safety, and it's important to get it right. The consequences of improper grounding can be severe, including electrical shock, fire hazards, and equipment damage. By following the NEC and working with qualified professionals, you can ensure that your electrical system is properly grounded and safe. The information provided is for educational purposes only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or engineer before performing any electrical work. Now let's discuss further the specific NEC sections that apply to the scenario. NEC 250.50 covers grounding electrode systems and requires that all grounding electrodes that are present at each building or structure served be bonded together to form the grounding electrode system. This bonding is typically accomplished by using a bonding jumper, which is a conductor that connects the various grounding electrodes together. The purpose of this bonding is to create a low impedance path for fault current to flow back to the source, which helps to trip the overcurrent protective device. NEC 250.52 lists the various types of grounding electrodes that are recognized by the NEC. These include metal underground water pipes, metal frames of buildings or structures, concrete encased electrodes, ground rings, rod and pipe electrodes, and other listed electrodes. As we discussed earlier, NEC 250.52 A7 specifically addresses rod and pipe electrodes and requires that they be driven into the earth at least 8 feet. If a single rod or pipe electrode does not have a resistance to ground of 25 ohms or less, it must be supplemented by an additional electrode. NEC 250.53 provides additional requirements for the installation of grounding electrodes. It specifies the depth at which grounding electrodes must be buried, the spacing between multiple electrodes, and the requirements for connecting grounding electrode conductors to grounding electrodes. NEC 250.64 covers the installation of grounding electrode conductors. It specifies the routing requirements for grounding electrode conductors, the methods for protecting grounding electrode conductors from physical damage, and the requirements for connecting grounding electrode conductors to grounding electrodes and service equipment. NEC 250.66 provides tables for determining the minimum size of grounding electrode conductors based on the size of the service entrance conductors. The size of the grounding electrode conductor is critical for ensuring that it can safely carry fault current back to the source. NEC 250.68 covers the connection of grounding electrode conductors to grounding electrodes. It specifies the types of connectors that are permitted for use, the methods for making connections to grounding electrodes, and the requirements for ensuring that connections are mechanically and electrically sound. NEC 250.70 covers methods of grounding electrode connection. The grounding electrode conductor must be connected to the grounding electrode by exothermic welding, listed lugs, listed pressure connectors, listed clamps, or other listed means. The connection must be accessible. The importance of proper grounding cannot be overstated. A properly grounded electrical system is essential for safety and for the proper operation of electrical equipment. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip the overcurrent protective device and prevent electrical shock and fire hazard. Grounding also helps to stabilize the voltage to ground during normal operation, which can improve the performance and reliability of electrical equipment. Therefore, it is crucial to understand and adhere to the NEC grounding requirements. By following these requirements and working with qualified professionals, you can ensure that your electrical system is properly grounded and safe. Let's revisit the original scenario and address any potential points of confusion. The question specifically mentions a number 4 bare grounding electrode conductor from the panel board to the concrete encased electrode in the footer. This is a common practice and is generally acceptable under the NEC. However, it does not negate the requirement for a grounding rod at the meter socket. The concrete encased electrode serves as one component of the grounding electrode system, while the grounding rod at the meter socket serves as another. Both are necessary to comply with the NEC. Some people may argue that the existing concrete encased electrode is sufficient and that a grounding rod at the meter socket is redundant. However, the NEC is clear on this point. The service equipment, which includes the meter socket, must have its own grounding electrode. This is because the meter socket is the point where the electrical service enters the premises, and it is therefore considered a critical part of the grounding system. The AHJ is responsible for enforcing the NEC and has the authority to interpret the code as it applies to specific situations. In this case, the AHJ has determined that a grounding rod is required at the meter socket, and their interpretation is supported by the NEC. It is important to respect the authority of the AHJ and to comply with their requirements. If you disagree with the AHJ interpretation of the code, you can appeal their decision through the proper channels. However, it is generally best to comply with their requirements in order to avoid delays and potential legal issues. It is also worth noting that the NEC is updated every 3 years, and the requirements for grounding may change from one edition to the next. Therefore, it is important to stay up to date in the latest edition of the NEC and to consult with qualified professionals to ensure that your electrical system complies with all applicable codes and regulations. In addition to the NEC, there may be local codes and regulations that apply to grounding. These local codes may be more stringent than the NEC, and it is important to comply with them as well. The AHJ is responsible for enforcing these local codes and can provide guidance on their requirements. When in doubt, it is always best to err on the side of caution and to install a grounding rod at the meter socket. This will ensure that your electrical system complies with the NEC and with any applicable local codes. It will also provide an extra measure of safety and protection for your home and family. Finally, remember that grounding is not a one-time task. It is important to periodically inspect your grounding system to ensure that it is still in good condition and that all connections are secure. If you find any problems, such as corroded connections or damaged grounding electrodes, you should have them repaired or replaced by a qualified electrician. By taking these steps, you can ensure that your electrical system is properly grounded and safe for years to come.